Good morning. Welcome to this Conservation Applied Research and Development, or CARD webinar today, reviewing results from a field study of advanced controls for residential heating, ventilation, and air conditioning fan. Thank you so much for joining us today. I'd like to cover a few housekeeping items before we start. All attendees will be in listen-only mode. We will answer all questions at the end of the presentation, but as questions occur to you, please type them into the Q&A box and send them to all panelists. The Q&A box can be opened by clicking the ellipsis in the lower the lower right of your screen as indicated on this slide. We will do our best to answer all questions within the time allocated, but if we don't get to some, we will answer them after the webinar. This webinar is being recorded and will be available on the department's website. The slide set and script from this webinar will be emailed to all registrants within 2 weeks of the webinar. And finally, if you'd like closed captionings on this webinar, click the CC bubble on your screen. I am Lindsay Anderson, the Utility Energy Conservation Research Planner at the Minnesota Department of Commerce within the Division of Energy Resources, Energy Conservation and Optimization Business Unit. In that role, I identify and analyze gaps within utility energy conservation and optimization programs and coordinate and plan research to fill those gaps. The CARD program is a major tool of that work. With me today is Lauren Sweeney, a Principal Energy Planner within the Energy Conservation and Optimization Business Unit at the Department of Commerce, where she specializes in the regulation of electric and gas utility energy efficiency, load management programs, as well as is the staff lead on the technical reference manual. She was the project manager of the research that is the subject of today's webinar and will be moderating the Q&A portion of today's presentation. Our presenters today are Grant Baumgartner and Mason Miller from Center for Energy and Environment. Grant Baumgartner is a research engineer at CEE, where he conducts research on emerging technologies in HVAC and refrigeration systems. Prior to joining CEE in 2022, Grant spent 6 years developing commercial HVAC and transport refrigeration products. We also have Mason Miller, who is a research analyst at CEE, where he deploys data monitoring equipment and provides data analysis for CEE's various energy efficiency research projects. Welcome, Grant and Mason. We look forward to your presentation today. This webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goals. $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from the CARD projects provide utilities with data to enhance energy efficiency program designs within their energy conservation and optimization portfolios. As you can see by the pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is the residential sector, and the presentation will discuss results from a recent CARD project to measure the savings potential and characterize the market for a commercially available fan controller to increase the efficiency of residential heating and cooling systems. With that, I will turn it over to Grant for today's presentation.
Thanks, Lindsay. Hi, everyone. As said, my name is Grant Baumgartner. Today, Mason and I will be presenting our research on the advanced controls for residential HVAC fans. In today's presentation, we'll provide some background on the fan control technology, then go over our process and our findings from the major project steps. Those project steps included market characterization, modeling, and a field evaluation. The modeling work was intended to independently estimate the savings potential of the device and identify site characteristics that correlated with increased savings. The market characterization assessed past HVAC research in Minnesota to estimate the statewide savings potential, confirm those modeling inputs, and ensure the field sample represented the HVAC systems in the state more broadly. The largest portion of the project was the field evaluation phase, which consisted of a detailed evaluation of the heating and cooling performance of HVAC systems with and without the fan controller in 24 single-family homes and townhouses. Moving into the background, we'll first start with a quick refresher on forced air heating systems. So in these systems, air from the conditioned space is drawn through the return air plenum and a filter by the blower fan and passed over a heat exchanger. The inside of the heat exchanger tubes are heated by gas combustion, and then warm air is distributed by the supplier plenum passing over the outside of that heat exchanger to the supply registers. So the combustion products are exhausted out of the building envelope, and that's essentially how these furnaces work. Here we want to illustrate the effect that the device we studied has on a typical heating cycle, and that is shown in these two time series plots. The top plot shows the return and supply air temperatures measured before and after the furnace heat exchanger in blue and red respectively. The bottom plot shows the voltage measured by a current transducer that's clamped around the gas valve and the fan wires. In a typical cycle, the gas valve will turn on to start combustion and allow the heat exchanger to heat up. And then within about 30 seconds, the fan turns on to circulate air through the heating system. Once the thermostat call for heat is satisfied, the gas valve will close to stop combustion, and the fan will continue to run to cool the heat exchanger and continue distributing heat to the home. A small change in fan current was detected at the point where the built-in furnace controls normally de-energize the fan, so that's about 120 seconds or about 2 minutes after the gas turns off. The fan controller that we studied extends the fan runtime for a few minutes beyond that default fan off point. And during this extended operation, heat that would not normally be transferred from the heat exchanger via forced convection is pushed into the duct system by the fan. There are a few of these commercially available controllers that claim to reduce gas and electricity use of forced air heating systems and cooling systems. The device we tested was the GreenFan Smart Fan Controller. It's pictured in the left, and it's shown in one of our field installations on the image in the right. Throughout the presentation, I will be referring to green fan mode and base mode, where green fan mode means the operation of the furnace with the controller active, and base mode means operation of the furnace in its default configuration. The manufacturer of this device claims it saves 334 kilowatt hours of electricity annually and 21.7 therms per year of natural gas, depending on site-specific characteristics in the context of the building. And that's based on both simulations as well as lab and field tests. This device is an approved energy conservation measure in the California Technical Reference Manual. And this, as I said, the unit energy savings for that measure are going to be, they are based on lab testing that evaluated the device's impacts on cooling and heating. One of the major goals of this project was to verify the claimed gas savings, since this product had not yet been tested in a cold climate. So getting into the theory behind this device, the theory behind the claimed savings is that by improving the distribution of heated or cooled air from the air handler, that the furnace or the AC can remain off for longer between cycles, and that over time, this slight extension in idle time could lead to fewer operating hours for the HVAC equipment and reduced overall energy use. So this effect is shown in the illustrative example plots here on this slide. And the plot on the left, the cycles are about the same length between base and green fan mode, but the space between the green fan on cycles is extended. And then when you take that cumulatively, gas is on for less total time over a sufficiently long window. So in the plot on the right, we have an hour of time, and you can see as time passes, as the idle time between cycles is extended for green fan mode, it will use less gas in the long run in this kind of simple illustrative example. As the last bit of background, I want to briefly discuss our primary research questions. Each of these project steps that we talked about in the beginning was designed to answer these specific questions. So through modeling, we assessed whether there was a theoretical basis for energy savings. Through the market characterization, we sought to understand the characteristics of the residential HVAC equipment in Minnesota. And through the field evaluation, we quantitatively analyzed whether the HVAC system in each site used less energy with the fan control device active or not. So moving into the modeling section, we created a time domain model of a home heating system to understand the energy savings potential of the device. The system model consisted of a state machine feedback controller, which represented the thermostat, a first order transfer function that represented the furnace, and a lump capacitance model that represented the home. The model was designed to accept several different configuration parameters, which enabled us to tune the model to simulate different performance of heating or cooling systems, heating systems for this model of the various homes in the sample. Inputs to the thermostat model were the temperature set point schedule, a temperature deadband, and the indoor temperature which was the feedback signal. The thermostat compared that feedback signal to the set point and used a simple hysteresis-based control to determine whether the furnace should turn on or turn off. Upon entry into a new state, the thermostat model would log the simulation time and the initial supply air temperature, which it passed to the furnace model for furnace model's use. The thermostat was responsible for turning the fan on upon entry into the on state, but the model that turned the fan off was the furnace, so that the furnace fan off delay could be provided to the system model as a configurable parameter. After the thermostat, the system model, as I mentioned, executed the furnace model. So this involved calculating the furnace heating capacity from the return and supplier temperature difference and the fan state. Fan provided the airflow. The fan was assumed to be on if the furnace was on, and if the furnace was off and it had been off for less than the time specified in the fan off delay configurable parameter. So crucially, in the furnace model, we assumed that the heat capacity was zero unless the heating capacity, was zero unless the fan was on. Finally, energy balance calculations were carried out by determining the heat loss from the house as a function of the indoor-outdoor temperature difference and looking up the estimated internal gains from the assumed internal gains schedule. Net heat transfer to the home was modeled as the sum of the furnace input, heat loss, and internal gains. So the model was designed to accept time domain inputs such as ambient temperature, thermostat schedules, and internal gain schedules. And we did that so that we could minimize the sources of error between the model and actual field data. As you can imagine, these schedules had a major effect on the modeled furnace cycling behavior. And it's important to remember that two of them are estimates. So while it's possible to fine tune those schedules so that the modeled energy delivered by the furnace matched the actual energy delivered on any given day within a few percent or even 1%, the model was primarily used to isolate the effect of the fan delay parameter on the energy delivered per cycle and per day after tuning the model to plausible scenarios. The graphic here is showing this. Sorry, could you go back? Yeah, thank you. The graphic here is showing the supply air temperature and how we are able to match, qualitatively match the actual temperature in red with the model temperature in blue. Next slide. We used the model to run sensitivity analysis. I'll get into that here in a second. We'll talk about first the way we generated simulation input parameters. We sampled those randomly from uniform distributions. We had different distributions for time constant of the furnace, house capacitance, house heat loss coefficient, and constant daily ambient temperature. The parameters for temperature gain and airflow for the furnace were also randomly sampled, but we checked that combinations of those parameters made sense as a reasonable furnace heating capacity. The sensitivity to those input parameters was estimated by running pairs of daily heating system simulations with all of the input parameters fixed except for the fan delay. So for the fan delay parameter, we used 120 seconds to represent the baseline system behavior and 300 seconds to represent alternative system behavior under the effect of the fan controller. To visualize the sensitivity of gas savings to each input parameter, then we plotted the relative savings, so that's the percent savings for each simulation case against each input parameter. And then the sensitivity analysis indicated the greatest opportunities for homes with large furnaces relative to the heating load. And we sort of got to that conclusion by assessing the slope of the regression lines on these plots. So the slope of the regression line indicates positive or negative correlation between savings and input parameter. And the spread of points about the regression line indicates kind of the uncertainty in the impact of the parameter. So the qualitative analysis showed that savings increased with increasing furnace airflow, temperature rise, ambient temperature, and furnace time constant. And that matches our intuition that if more heat is available from the heat exchanger, extending the fan runtime should reduce gas on time. And then for the two with negative correlations, savings decreased with increasing home heat loss coefficient and capacitance. And this also matches our intuition because larger heat loss means the furnace would tend to be on a larger fraction of time and cycle less. So the relative impact of the fan delay is smaller. And then for larger capacitance, same idea. The temperature in the home changes more slowly. So the furnace would tend to cycle less and reduce the impact of the fan off delay. After that first pass analysis where we used uniform distributions of input parameters, we then resampled input parameters from distributions that represented prevalence in Minnesota. So that first pass was useful for sensitivity analysis and sort of estimating the maximum range of savings, while the second approach, we could use that to estimate the most likely distribution of savings in Minnesota homes. Using those representative distributions of input parameters, the overall results were similar to the results using the uniformly distributed parameters, and kind of point out a couple of specific results. The median decrease in gas use and cycles per day for the 1,000 simulated cases was about 2%, and the median increase in fan runtime was about 8%. And the median change in capacity delivery was about 0%. So now I'll turn it over to Mason to discuss the market characterization.
Thank you, Grant. We reviewed past HVAC research characterizing furnaces in Minnesota, compiling past research with additional outreach conducted as part of this project. We found that most furnaces installed in Minnesota today are 90% efficient or better. The most common first stage input rating is between 60 and 80,000 BTU, with roughly equal numbers, slightly smaller or larger, and a handful of very large furnaces. The largest source of HVAC system data came from the CARD-funded Improving Installation Project report. The other main source was the Retrofitting Forced Air Combi Systems report prepared for the National Renewable Energy Laboratory on behalf of the U.S. Department of Energy's Building America program. Both of these papers are available through the links in the slides, and we also supplemented this data with research we did in 2018 as part of a pilot study on the fan control technology. Data from past Minnesota HVAC research indicated a tight range of fan off delays. Of the 84 furnaces tested in the quality installation project, all but 2 furnaces had fan off delays of at least 90 seconds. The longest observed delays were up to 180 seconds. From the 20 sites assessed as part of the pilot study, the longest fan off delay observed was 150 seconds and the shortest was 0 seconds. However, the manual for the furnace with the 0-second fan off delay indicated that the configurable range for this setting was 90 to 180 seconds, implying that the observed value of 0 may have been due to a furnace controls malfunction. The advanced fan controller extends heating fan off delays up to 300 seconds, indicating some savings potential on all the systems that were evaluated. And then temperature rise, or the steady state difference between supply and return air temperatures, was between 40 and 70 degrees in over 80% of assessed furnaces. We interviewed 5 furnace distributors to learn about the market and their opinion of aftermarket fan controllers. They noted that 90% efficient furnaces comprise the majority of the furnaces they sell. Some of the distributors were familiar with the fan control devices, and those that were familiar saw potential for the device. However, they cautioned that the market and window of opportunity for this device was shrinking, as the best applications for the device were middle-aged standard efficiency furnaces. Some also were concerned that cooler air distributed at the end of the heating cycle could cause comfort complaints. And then next, I'll get into our field evaluation approach. As shown, our monitoring package included 2 loggers at each site in each of those pictures. The left image shows an example of the logger deployed at the air handler, and the right image shows the power meter logger deployed at the breaker panel. We monitored supply and return air temperatures along with gas valve and supply fan currents from the air handler. From the electrical panel, we monitored AC power and air handler power. We also took airflow measurements that were recorded for each cycle of each available operating mode at the time of the monitoring package installation. This photo shows the physical setup of the relay with the fan controller. The 24-volt transformer shown in the top right of the photo was plugged into a Wi-Fi enabled smart outlet, which allowed remote activation or deactivation of power to the transformer. In series with the relay, this allowed us to switch between baseline air handler operation and fan controller active operation. The mode of the system was typically changed every 2 weeks. And then a little more detail on the relay system. The default non-powered configuration of the relay is activation of the 1 and 2 terminals, which activates the fan controller. Provide power, and the relay changes connection to the 3 and 4 terminals, bypassing controller operation. These detailed diagrams are nice for showing how the relay switches the fan operation between baseline and fan controller mode based on power status of the smart outlet. And then with that, I'll turn it back over to Grant for the field analysis results.
Thanks, Mason. We tested the fan controller at 24 sites located primarily in the Twin Cities region. The sites all had forced air heating systems, which spanned a range of sizes and floor plans. Furnace configuration was pretty consistent, with 16 sites having a measured base mode fan off delay between 100 and 150 seconds. Our study included more 80% efficient furnace than is really representative of the market, but this overrepresentation we deemed acceptable because the savings opportunity was expected to be larger, maybe for those older 80% efficient furnaces. The size to load ratio also spanned a wide margin, but the most first stage ratings were on average about 2.5 times higher than our calculated design heating loads for each of those buildings. So throughout the results presentation, you'll notice that not all 24 sites are going to be included in each analysis, and this slide tries to explain which sites were included for which analyses. So site B was excluded from all the analyses because the HVAC system only ever operated in green fan mode. Due to site access issues, the alternating mode relay was never installed, so we don't have data on the baseline performance of the system. Sites E and S had communication issues early in the project, so very little data was collected during the heating season. However, both of these sites had sufficient data for the cooling analysis. Site H was excluded from all the analyses because the controller caused the air conditioner to short cycle pretty severely in cooling mode, so we did not leave the controller installed. We just skipped that site after testing it during the install phase. Then we also divided the work of installing the air handler monitoring equipment, which we did ourselves, and the work of installing the power meter, which was performed by an electrician, in order to facilitate scheduling these installations more quickly and growing the sample size during last winter. As a result, power meter installations for electrical monitoring lagged the air handler monitoring, and only 4 sites had sufficient heating season data to assess heating season electricity usage. The cooling analysis only included sites where we detected a clear, longer fan off delay in green fan mode relative to base mode. While the performance at those excluded sites was potentially affected by the green fan controller in the expected way, the results from our data processing routine showed either inconsistent differences or no difference in fan off delay between modes. So this figure shows box plots with the outliers hidden, describing distributions of fan off delay time is observed at each site by mode in heating season. So you'll notice at all sites except for site Y, the green fan mode fan off delay appears longer and more variable than the base mode. And this is the expected behavior of the controller. The median of all the median fan off delays across sites is 120 seconds in base mode and 287 seconds in green fan mode. For base mode, 18 of 20 sites had a median fan off delay between 100 and 150 seconds inclusive, while the median values for the fan off delay in green fan mode ranged from 203 to 334 seconds, except for site Y. So while site Y appears to have a non-functioning green fan mode, we confirmed expected operation by plotting time series current signals for the fan and seeing that it was more of a quirk of our data processing routine that wasn't able to pick up the additional time associated with the fan off delay. And as I mentioned on the last slide, you'll note that sites B, E, H, and S had insufficient data to include in this analysis due to communications issues, compatibility issues, or site communication issues. So now in cooling mode, the fan off delay, same graphic, same type of graphic, but the cooling season performance of the controller is shown. We expected smaller than gas savings in Minnesota's climate, smaller cooling savings than gas savings. So we focused on sites where the observed performance of the fan controller matched our expectations following this first pass data processing routine, and decided to defer the work of reconciling the data processing and labeling issues until we found evidence for savings associated with green fan mode. So for example, site D showed clear difference in fan off delay associated with green fan mode, while site C did not. It's possible that the controller is functioning as intended for all these sites and that our data processing routine is the reason that we didn't see the expected performance here, but as I mentioned, we just focused on the 10 sites from the cooling analysis that showed clear differences in fan off delay. Okay, so now we're getting into the quantitative analysis of the fan controller performance. To quantify the impact of the fan controller on gas use, we use linear regression models of energy use as a function of heating or cooling degree days and control mode. So heating degrees are defined as the difference between the balance point temperature and the daily average outdoor temperature. The heating balance point temperatures were identified in this study as the daily average temperature on the warmest day where furnace gas use was detected. Cooling balance point temperature was taken as a change point of a piecewise linear regression model that we fit to electrical energy versus outdoor temperature. Each site had that multiple linear regression models fit to the observed daily average data, and these plots show those predictions of those linear regression models overlaid on the observed data. So the points, each point represents 1 day of operation, and the lines represent the model predictions as a function of heating degrees. You'll notice, as is always the case, the real data is noisier, and we'll talk about that a little bit more later. So as I mentioned, the independent variables were heating or cooling degree days and control mode. This approach allowed us to directly assess the statistical significance of the control mode variable. In most cases, so 14 out of 20 cases, we found that there was not enough evidence to say that that control mode predictor was different from 0. So graphically, this is indicated by the fact that the slope of the regression lines associated with each mode appear virtually identical. So like for site C, for example, for each of these sites, there's a pink line and a blue line plotted. And for most of the sites, they're right on top of each other, so you can't really see the pink line. To quantify the magnitude of the impact of the fan controller in meaningful units, we calculated typical annual gas use using the models we developed on the last slide, and then the TMY3, the typical meteorological year 2020 data for Minneapolis, St. Paul. And even though the prediction confidence intervals are relatively small, in most cases, they still overlap between modes, which is another way to see that the effect of the controller was not statistically significant. For reading these charts, it might be helpful to note that one therm is roughly 100 kBTU. So if you kind of move the decimal point over 2 spots to the left on the y-axis scale, that would be therms. And we highlighted a few examples on this plot to show where the estimated annual gas use with green fan mode was the same as base mode, or less than base mode, or more than base mode. But again, 14 out of 20 sites, the predicted gas use with and without the fan controller was the same. So while we were unable to detect a consistent decrease in gas use associated with green fan mode, we did see consistent increases in fan electricity use. So we, again, used that same approach, fitting regression equations. This time we fit them to the daily total air handler electrical input as a function of the daily average temperature and mode for 4 sites. So those are the 4 sites that had sufficient heating season data. And this is what the regression plot looks like when there is a significant difference between modes. You have slopes that differ between base and green fan mode. And the steeper slope of the green fan mode means that as that the green fan mode uses more electricity at a given temperature. Using, again, the TMY3 2020 weather data to predict the annual furnace electricity consumption for heating mode, for heating by mode, produced the results shown in the bar plot. So the significance of these coefficients was statistically significant in each case, meaning there's a statistically significant difference in electricity use. In this case, on average, the sites used 122 additional kilowatt hours per fan operation throughout heating season, which is about a 27% increase. As I said earlier, we considered that Minnesota is a heating-dominated climate, and most of the market characterization, modeling, and field analysis as a result focused on heating season performance. But the same analysis techniques were also applied to the cooling season data. We found that extending fan runtime in cooling mode had no statistically significant impact on air conditioning energy use. The impact of the air conditioning electricity use of extending the fan off delay was much smaller than that of the sensible cooling load, and apparently much smaller than other unmeasured factors. So some sites showed statistically insignificant savings, while others showed statistically insignificant increases in energy use, but there's really no evidence to support that the effect of the fan controller on air conditioning energy use is non-zero. And as in the heating season, we expected a small energy penalty due to increased fan runtime associated with green fan mode. And in practice, the effect of that fan control mode on fan energy as a function of the sensible cooling load was only statistically significant for 2 of the 10 sites. So the same unmeasured factors from heating season, solar heat gains, occupancy, occupant behaviors, things like cooking or changing the set point, opening doors and windows, apply to cooling season also, but cooling season loads are also heavily impacted by latent cooling loads associated with humidity in the air. So I think that was part of the reason we saw even less correlation of the energy use data with the fan control mode and cooling season. So moving on to kind of the wrap up here, discussion and conclusion. For 14 of 20 sites, most sites, they exhibited no significant difference in gas use with green fan mode. For these sites, the uncertainty associated with the estimate of that interaction term, that term associated with the control mode, was large relative to the value of the estimate. So in physical terms, that means that there are other factors that affect daily gas use that have a far greater impact than fan off delay. And as I mentioned on the last slide, they show up as sources of uncertainty. Could be things like solar gains, occupancy, and occupant behaviors. For the sites that showed increases in gas use, it's possible, there are 3 of these, for these 3 sites, it's possible that return duct leakage allowed cool air from unconditioned basements to be drawn into the duct system through this extended fan runtime and distributed to the area around the thermostat, which actually reduces the time between furnace cycles if the thermostat thinks it's colder than the average temperature of the house actually is. And then for the sites where the device saved energy, it's possible that the heat exchangers of these furnaces provided efficient, highly effective heat transfer to the airstream, and the other characteristics of the air distribution system maybe caused the temperature near the thermostat to remain elevated between cycles, which is the design of the device. And it maybe did perform the intended function of extending the time between cycles. But again, that was only in 3 of 20 cases, and it was just as likely to see cases where energy use actually was increased through the use of the fan controller. So circling back to the research questions that we introduced at the beginning of the presentation, the modeling exercise showed that extending fan runs times to improve distribution of the heating capacity could theoretically lead to long-term savings, assuming that ducts are perfectly sealed and no residual heat from the heat exchanger migrates to the conditioned space on its own, that it requires that the fan is running. We found that there's little significant variation in furnace characteristics and configuration across the state. They're typically installed with factory settings and rarely adjusted. Newer equipment is generally highly efficient condensing furnaces, while older equipment is more likely to be 80% or standard efficiency furnaces. That the theory that distributors floated that the fan control device would make the most sense for kind of middle-aged furnaces, these newer standard efficiency furnaces, was not really supported by the field evaluation. And in practice, we have lots of field data, and despite that, we can't say that the fan control device reduces gas or electricity use. In fact, we say that it increases electricity use in heating season in Minnesota. And that is it for us. Thank you.
Thank you, Grant. That was a great presentation of the work that you all did, you and others at CE did for this CARD project. Audience attendees, if you have not already done so, please type any additional questions or questions that you have in the Q&A panel and send them to us as we transition into the Q&A portion of today's webinar. With that, Lauren, do you have any questions for Grant or Mason?
Yeah, so I'm seeing a question from Kurt. He said, has a report been published on the CARD website?
I can take that. No, the report has not been published on the CARD website. And Lauren and or Grant, can you walk through the remaining timeline of the contract and delivery of the final report?
Yeah, so that is something I can do. The contract is expected to be closed out at the end of March. And then we expect that CARD project, the CARD report to be published on the website soon after. And then if you email folks at the department, so any of the 4 people listed at the beginning of this presentation, we can send over that finalized CARD project as soon as it's made available, even if it's not on the website. Awesome. Kurt, do you feel as though that was sufficient, or do you have any follow-up questions? Okay, so I'm seeing a next question from Christopher, and he said, why was this device selected?
I may have to lean on Mason for the answer to this question as well. I came into the project as it was about a year into its journey, so I wasn't around for the selection of this particular device. My understanding is that because it was had been lab tested and field tested, kind of part of the California TRM, there was interest in seeing if it was a good fit for the Minnesota as a direct install measure, potentially as a way to capture gas savings.
Awesome. Appreciate it, Grant. Kurt, thanks for your follow-up note. We did have a question that was submitted earlier, and it's, can you elaborate on why the modeled savings didn't show up in the field study?
Sure. So as I mentioned, we made kind of the best case assumptions, like on behalf of the device in the modeling. That is, we assumed there was no heat transfer from the HVAC system into the conditioned space unless the fan was running. And we know practically in Minnesota, some of the energy that's going to be stored in that warm furnace heat exchanger is going to naturally migrate to the space, especially if those ducts are in the basement. And the field study results suggest that maybe the majority of the energy that's in the heat exchanger actually stays in the building envelope. So the additional fan runtime doesn't practically seem to have an impact on the gas use.
Awesome, thank you. Victoria mentioned, would there be a benefit to installing on less efficient furnaces that may appear in older low-income buildings, or would it make more sense to use funds to replace inefficient furnaces?
I can speak to the first part of that. We definitely had older furnaces that I think one of our furnaces was even close to 50 years old in their sample of 24. And based on the statistical analysis, there doesn't seem to be any correlation between furnace age or furnace type and savings. Like we saw savings, like significant savings and significant increases in gas use at two furnaces that were seemingly identical. So I think that it's difficult to quantify the factors that actually would result in savings. And the main point is most of the time this device would not result in any savings. So I don't know maybe what the best use of the funding would be, but I would say this device is not probably the place to invest if you're looking to capture gas savings in low-income properties.
Awesome, thank you. I'm seeing another question from Samantha Hill. She said, did all of the monitored sites have a basement furnace location? I wonder if the generally colder furnace location was a significant factor in lack of savings.
I'm trying to think. I think that is the case. We definitely had some split level houses where it was like a walkout basement that's sort of like a hybrid basement, first floor type design, but I don't believe we had any that were, like in the upstairs or the conditioned space, primary conditioned space, living area.
Cool, thank you. Cindy asks, do we know the preventative maintenance history on these older units?
We did not look into that as part of this project, so fortunately, no.
And Chris follows up with, what was the total cost of this study? That's a question I can answer. And let me pull it up. Give me just a moment. And actually, while I do that, there was another question that was submitted a little bit earlier, and it said, this device is an approved energy conservation measure in the California Technical Reference Manual. What about the California measure or the homes and HVAC equipment in California make this technology viable as an efficiency measure there, but not viable here?
Good question. So this measure in the California TRM references the lab tests that we reviewed as part of this project. The lab tests make pretty much the same assumption that our model did, namely no heat transfer to the conditioned space occurs unless the fan's running. And as we've discussed, the location of Minnesota ducts typically means that there is some thermal communication between the basement and the house, and that assumption is not valid. So California homes may have other configurations with supply ducts that are outside of the conditioned space, for example, in attics, where that assumption would be more accurate. So in addition, I think it's important to point out that the lab tests did highlight this correlation. The lab tests that were done as referenced in the California TRM say that the savings potential for the device is greatest with smaller part load ratios. So part load ratios, they define as the ratio of the amount of energy delivered to the maximum possible amount of energy delivered. So we sort of looked at furnace size to load ratios, which would be the inverse of that, but the idea is the same. That is, if the furnace is really oversized for the climate or for the building, then there's a better opportunity for savings in theory. And with California's milder climates and a greater portion of their building stock being served by potentially oversized equipment, then this device might be more suitable in that context.
Awesome, appreciate it, Grant. I have one more question that was submitted prior to this this webinar. I'm not seeing any additional questions come through, so I'll ask this final question. But just want to give another shout out that if you do have a question, please put it in the chat and we'll get to it. So the last question that I have is: has this technology been studied in Minnesota or climates similar to Minnesota's climate previously? And then what are the differences between this study and past studies?
Good question. So past studies of this device occurred at lab facilities in Texas and at field sites in Nevada. So to our knowledge, the device has not been studied in a cold climate. Another major difference between our study and past research was the duration of the monitoring period. So we monitored system performance at 24 sites for a year, while the lab tests and the field test ranged from about 1 to 10 hours in duration. So if you think back to that grid of plots, the scatter plots, we sometimes saw at the same temperature, green fan mode would use less gas than base mode and vice versa. So just with many more samples we had by monitoring for a much longer period, I think we have a lot of confidence in our results that if there was long-term gas or electricity savings associated with this device, we would have seen it.
Lovely, thank you. And I do want to go back to a question that Chris posted, or Christopher posted. He asked what was the total cost of this study, and it was about $290,000. It is noted within the chat, but I did want to call it out just for folks who are listening only. And I'm not seeing any additional questions come in, but as they come in, or as you think about them, feel free to reach out to Grant Mason, Lindsay, or myself, and we can get those questions answered.
Great. Thanks, Lauren. Thanks, Grant. I do see, I don't think we did address one more question. I don't know if it was just sent my way or if it was sent to the team. I'm just going to touch on that one quick before transitioning to closing slides. Were any non-energy attributes measured within the project? So humidity, temperature distribution within the home, any type of qualitative assessment of homeowner comfort changes, anything else?
Yeah, that's a good question. We did do a homeowner comfort survey that we administered kind of 4 times. So twice in cooling season, twice in heating season, and then one each in, or so, cooling green fan, cooling base, heating green fan, and heating base. And we didn't disclose to the occupants what the active fan control mode was. And we asked their perception of, like, how do you think your fan is running relative to typical, longer, shorter, the same, or can you just describe the quality of the air from your supply registers? Trying to tease out the concern that some of the distributors that we interviewed shared, that if cold air from supply registers was being forced into the space at the end of a heating cycle, people might complain about discomfort. And what we found was that people really couldn't tell if the device was on or off. We had answers in both directions for both base mode and green fan mode. If my fan is running longer than normal, shorter than normal, the air is the same, I feel comfortable. Pretty much, I think the consensus was everyone felt reasonably comfortable with their HVAC system. So no qualitative changes were really detected by the occupants.
Okay. I don't see any more questions coming through. Lauren, do you see any other questions coming through?
I have not.
Okay. Okay, great. Well, then with that, I will transition to the closing slides. to wrap up the webinar. So thanks again for your presentation, Grant and Mason, and thank you, Lauren, for facilitating that Q&A. And as Lauren said, please do reach out to Grant and Mason with further research questions, or her or I to follow up in regards to final deliverables or accessing research results and things like this. On that note, this slide set will be emailed to all webinar registrants within a week or two of today's webinar. So you'll have the slides and the transcript from the webinar. The webinar recording, as well as the slide set, will be made available on the department's website along with the final report in a couple of months. When available, you can link to either of these from the quick links on our Applied Research and Development webpage as indicated on this slide. The department's R&D webpage has additional resources and information related to the CARD program and to CARD research projects, which you can check out by going to the web address in the middle of the slide. The CARD website rebuild is now complete. So to access research before 2020, use the web links on the left panel of the web page. And to access research since 2020, which would include this project, navigate to the through the blue button in the center of the web page, and you'll find a searchable site that lists all of the projects and final deliverables related to those projects there. Although the CARD website rebuild is now complete, there are ongoing efforts to ensure that all the research is posted. So if you are trying to access a final report, a slide deck, a webinar of a project in there, please do not hesitate to contact me if you cannot access what you're looking for, and we'll support your access of that information. Thanks to audience members for participating today. We appreciate your interest in CARD projects. I want to take a minute to mention 2 upcoming CARD webinars. On March 21st, Center for Energy and the Environment will be presenting their project on optimizing the new generation of grocery refrigeration equipment. And then also on April 25th, other research principal investigators, again from Center for Energy and Environment, will present on their project of ductless cold climate heat pumps for multifamily applications. So to keep aware of upcoming CARD webinars as they're scheduled and other news related to the Minnesota ECO program, you can sign up to the SIP listserv and receive updates through our email list. And there is a link on the slide deck that is sent out where you can access that, or let me know if you need help in accessing that sign up. And as other questions or suggestions come to mind in terms of CARD related to the CARD program or CARD webinars, please also don't hesitate to reach out to me. So with that, thanks for participating in the webinar today. That ends our webinar. Take care and goodbye.